You know, it used to be a time when physicists thought that particles were little chunks of mass. You know, the electron was a little chunk of mass that had a charge, you know, of 1 unit, and that was the theory. Now they've realized that that's not really a very good description, that the electron's really a point, and it really doesn't have any extent, and it really doesn't have any mass. It has the properties of mass. It has the properties of charge. And physics has learned that when it makes assumptions that are based in this being an objective reality, in other words, little chunks of mass, that they run into problems. That theory has holes in it and doesn't work. The experiments that they do tell them differently. So over the last decade, physics has been very quickly, actually, I think, moving toward seeing this reality as a virtual reality. 10 years ago, when I started on this path writing these books, no group of physicists would have been caught on public record talking about virtual reality. Now, 2012, last year, there were groups of very highly thought of physicists, you know, having panel discussions on at physics forums about virtual reality. So, you know, these are the top-notch schools, you know, the MITs and the Fermi Institutes and from all over the world, and the subject matter was, you know, reality as information and a virtual reality. That's the thing now, that's not kind of fringe physics anymore. That's become standard physics. The experiments tell us that that's the way it is. And they haven't gotten there easily. It's been a begrudging struggle against this particular conclusion. And they finally just have nowhere else to go other than to realize that reality is just information-based. And that's now making more sense to the traditional physicists. So I'm no longer out on the crazy lunatic fringe. I'm actually a part of the center now in terms of this. Now, they don't quite go as far as I do in that they don't understand how and why that works. They have no idea why this should be a virtual reality. They have no idea how it gets computed, how that information gets done. That's a big mystery. They just know that it's that way. They don't understand the consciousness connection yet, but that will come in time. So anyway, I want to talk a little bit about physics. The reason that the very first, let's put it this way, let's go back and do it historically. About 80 years ago was the beginning of the science of quantum mechanics, quantum physics. Everybody's probably heard the words and probably nobody really knows what they mean. But it started with a single experiment called the double slit experiment. And I'm going to explain that a little bit to you today so you'll get a little bit of the idea of why physicists are having this problem. And I'm going to use the board here. It's going to be rough, but hopefully you'll have good imaginations and you'll be able to follow me. Usually I project, you know, slides with 6 colors on them and it's all nice and pretty, but there's too much light in this room to use slides. It would be very hard for us to see them in such a bright, well-lit room. And actually, I'd rather have the nice, bright, well-lit room, you know, than the slides. So I'll do my best here to make this understandable to you. So this was called the double slit experiment, and that's because there was 2 holes, 2 slits in a barrier. So think of a barrier like my hand with slits in them, okay? So there's a barrier, and what they had known for years and years was that if they shine a light on this, if there's a light being shone on this, that over here on what we'll just call the screen, okay, we'll make that be the screen, that some of the light, here's kind of a light wave coming in, and the light wave's going this way, and part of the wave would go through here, which makes, you know, these little wavelets come through here, and part of the wave would go through here, these little wavelets like this, and the waves would interfere with each other. And the way they'd interfere with each other, that if this distance, let's say from here to this point, and from here to that point, if that distance was some integral number of wavelengths, okay, so that you can see this distance is going to be a little shorter than that distance, right? That should be intuitively obvious to you that this bottom distance has a little longer to travel than this one. Well, if that difference in those two distances was exactly one wavelength, or two wavelengths, or three wavelengths, then these two waves that look like there's a wave, they would get there exactly one wavelength apart, so they would be lined up. All right, you have two waves and you just shift them one wavelength, and they line up on top of each other. And when they do that, it's called, superposition of the waves, and you get a little spot of light there. And then here, of course, right across from the center, you'd always get a spot of light there because these two were always the same distance. So they both were, exactly in phase. And there'd be a point here where here was the first point, say, where they were just one wavelength apart, two wavelengths apart, three wavelengths apart, and so on. So you'd end up with these that's the central dot right here. You'd end up with these little dots of light, and it would be dark in between. And the reason it was dark in between, because in the middle, those were places where the two wavelengths were a half a wavelength difference in them. So you had one that, you had a wave like this, and then you had another one that was just the opposite. And what would they do when you add those together? They cancel each other out. So in between here, where the half-length distances are, you had black spots. So this is called an interference pattern, because these two sources of wave would interfere with each other and create these, they actually weren't spots. They looked like spots in my diagram, but they're actually little lines of light, because these are actually slits in the third dimension. But anyway, diffraction pattern, been known for decades and decades and decades. We understood light was a wave. Well, technology developed to the point that we could realize that light could be described in terms of particles. The particle was called a photon. And Einstein got a Nobel Prize for this, was the one that saw that light actually came in particles. And he did that with a photoelectric effect. He found out that light carried little discrete chunks of momentum, which means little particle. Okay? So now the thought was, well, if light's a particle, how do the particles distribute themselves like that to make these spots of light and dark? How is that possible? We kind of see it with waves. Each hole creates kind of a new source of the wave, and they interfere with each other. So they said, well, let's see. And they found a way, which now is easy to do. Back 80 years ago, it was very hard to do. But they found a way to fire just one photon at a time, a single photon. So rather than a whole beam of light, we're just going to put one photon, one little particle of light, if you will, at this thing and see what happens. Okay, now what they thought would happen, of course, if light's a particle, I guess this is getting messy. When light's a particle, you expect it to go through the slit and hit what's on the other side. So here's our slit again. Here, there's the hole. There's the hole. You expect a particle now to either hit and stop at the barrier, or, here's our screen, go straight through and stop here. That's what particles do, right? That's what Newton told us. Particles travel in a straight line unless interacted, with an external force. So that's what they expected to see. They didn't see that. What did they see when they sent a particle through? Now, they sent a lot of them, one and then another one and then another one, so they had to send thousands of them through, but one at a time. What did they see? They found this with this light, they found this diffraction pattern. And the idea was, how's that possible? How are these little particles of light hitting at these spaces, and why don't they hit at the spaces in between? That made sense as a wave, but as a particle, that just didn't compute. So they said, all right, we're going to, here's the central one. I don't know if I'm judging it right. And here's the like one wavelength difference, two wavelengths difference, and these are like a half a wavelength, 3 halves, 5 halves, that kind of thing. So it didn't make sense. So they said, well, let's see what's going on here at this slit. So they put a detector here, which I don't know what we'll say with the detector. We'll just make I'll put a D here. How about that? Well, I made a mess. Doesn't look like anything. We'll put a D here. Here's our slit. And here's a detector. Put a detector at this slit. We're going to put a detector at this slit. And we'll take this back. And we're going to detect what these particles do. So they put a detector there and they fired photons, one after another, after another, after another, and all the photons that went through, I'll just hold this maybe. All the photons that went through this slit, the photon came along, got a detection. We just got a photon here. What happened? It hit here, got a grease spot. All the photons that were detected as going through this slit went right through here and went like that. They acted just like particles. They said, well, what's up with that? The detectors must have done something, right? Because before, when they fired one at a time, they got a diffraction pattern. Now they fire one at a time and they know what slit each one went through. They could see it as it went by. Now they all pile up in these two piles. So the detector must have been doing something strange. So then they turned off the detectors, and as soon as they turned off the detectors, they got the diffraction pattern. Turned the detectors back on, and the particles piled up in one spot. Now that was interesting, huh? So then they said, well, we will see whether or not it's the detector doing it. Somehow the detector is interfering with that light or not. So they let the detectors there. They let the detectors continue to detect, but they just didn't keep the data. See, the detectors detect and send out information. The information is a photon just passed through this slit. Well, that detector was still detecting, was sending out the information. A photon just passed a slit, but nobody listened. Nobody was recording it. The data was basically lost. What do you think happened then? Well, when the data was not collected, they got a diffraction pattern. So suddenly, the data is not collected. Instead of getting this, they got this diffraction pattern with these, spots of light. So they thought, that's odd. All right, let's look at the data now. As soon as they looked at the data, they collected the data. So now they had the data. They got just 2 piles behind each slit, and that confused everyone. That was the famous double slit experiment, and that was the first time that the physicists of the day said, there's really something about reality that we don't understand. Something's going on here that just doesn't make any sense. So what happens is, what the explanation is, of course, is that we really don't know where these photons are. And besides, I'm talking about photons, and we all think, well, photon's kind of a magic particle, maybe it's just because the photon's weird. But the same experiment was done with electrons, and then with protons, hydrogen atoms, and then with bigger and bigger molecules. And the biggest one I know of that was run was with a thing called buckyballs, which is like a soccer ball configuration of carbon atoms. It's 60 carbon atoms in a molecule. It's a special molecule of carbon. And that's huge. That's massive. You know, when you talk about photons, you're talking about particles that don't have rest mass, and they're kind of different. But a buckyball is a big molecule, and it's very heavy, very massive molecule. So they put the buckyballs in here, and the same thing worked the same way. When you had detectors, when you knew which slit the buckyballs would go through, they just pile up in piles. But if you didn't know which one they went through because you didn't bother to take the information, then they would distribute themselves in a diffraction pattern. Okay, so what was understood then, this was the birth of quantum mechanics, that we could understand this. Schrodinger, Heisenberg, Bohr, 1918, 1920, 1925 is the time we're talking about. They said if we understand that these particles really aren't particles, that they're probability distributions. We'll just say, because we don't really know where these particles are. You know, photons, electrons, even buckyballs, it's not like you can see them. You make them, you kind of shoot them in that direction, but you don't really know exactly where they are because they're so small. So there's uncertainty. Uncertainty is a key. So he says because they're uncertain, we'll just assume that this is a probability distribution here, a probability that a particle will go through this hole. And because of the particle itself, if here's a particle coming, let me erase that, here's a particle coming, it actually has a probability distribution that it could be anywhere from, say, plus infinity to minus infinity. It has a certain probability everywhere. Now that probability is really small, and it gets bigger. It sort of looks like this. That's your probability distribution. So out here's maybe minus infinity, and out here's plus infinity. And there's some place in here at some position along the slit where it's got a maximum of probability where it probably is. So there's some probability that that particle would go through this slit. There's some probability that that particle might go through this slit. You see? There's some probability it could go through either one. And they said, well, if that probability then could interfere with itself, and there'd be a resultant probability here at the screen is where it would be most likely. What's the probability that probability going through here would interact with this probability, and the particle would end up here, and now you have a probability distribution here that looks sort of like that. That's your probability distribution when this probability, which comes in here and then has a long thing like that. Here's this probability. Well, I shouldn't make it like that. It comes in here and it's broad. It covers both of these slits. Okay, it could be here, it could be there. And let me try to not confuse you. So anyway, that was quantum mechanics. It was the idea that we'll pretend that these particles are just probability distributions, that the probability mixes, and when you do that mathematically, when you mix the probabilities, you end up with a diffraction pattern because the particle comes through. There's the highest probability that it'll land here. The next highest probability it'll land here, and a less probability that it'll land here. And in here, the probability is 0 that it'll land here and here and here. So you end up with a diffraction pattern, but it's all done in terms of probability. And it's all based on an assumption that there really are no particles, there's just probability distributions. Now, if you're as old as I am, you'll remember that when you were first in chemistry or physics or whatever, and you talked about an atom, they told you, well, it's like you got a basketball here, and that's the nucleus, and then you got an electron, and it's orbiting around. It's like a BB, a little marble, and it's orbiting around this big nucleus, and you definitely had orbits around things. And that was a little massy electron with a little charge, and it would go, well, if you're at least 20 years younger than I am, and probably most of you are, when you got to school, it wasn't like that. We have this nucleus, and then there's this electron cloud. Is that ringing? I don't know where in your education came, but they now talk about electron clouds. An electron cloud isn't really a cloud of individual electrons, it's a cloud of probability. probability that that electron is any particular point in any time now is just a probability cloud. So the electrons were thrown out. We don't have electrons anymore. We have probability clouds. And if you look at even an elementary school textbook now on physical science, you look at the pictures, there's no more little electrons going around nuclei. There's clouds, gray clouds, look like a bunch of gnats or something flying around the nucleus. So that's been the physics description of matter since the middle 1920s. That was a long time ago. Now at that time, physicists had no idea of why this should work, this idea that particles were probability distributions, but what they found out is if they used that as an assumption, they could do calculations on what happens when you slam particles together and other sorts of things, and their calculations were right. They actually could predict what would happen when these particles slammed into each other. That was called the science of quantum mechanics. It was a real big deal, and it's probably one of the most successful theories that physics has ever generated. They're very good at predicting the outcome of these subatomic events. And why is that important? Well, these subatomic events is what creates atomic events, which is what creates molecular events, which is what we're all made of. You know, it's who and what we are. This is our world. This is our physical world. All starts from a bunch of probability distributions at the base. Now, see, that's weird physics, right? And physicists would tell you that. You know, we can quote Richard Feynman, one of the best quantum mechanics theorists that has come around for a while. He's a very, very bright guy. And to quote Feynman, when he was talking to his graduate students, and his graduate students would say, Dr. Feynman, well, what is this? This doesn't make any sense. What do you mean probability distributions? And quote, Dr. Feynman said, just shut up and calculate. And he's also said things, of course, like, nobody understands this. Nobody probably ever will understand it in the sense of what we mean by understand, you know. It's just impossible. So physicists, traditional physicists, 80 years ago, came to the conclusion that you just never figure this out. Just shut up and calculate. Because you can get the right answer, but we have no idea why. Well, now we have a good idea why. This is a probabilistic statistical reality frame. Everything is probable. There's all sorts of probable realities. I'm going to talk a little more about the probable realities after I show you this. And when you make a measurement, right, whether you look into the woods and see that there's a dead tree wobbling, or whether you look into the sky and see what's out there in the universe, or whether you look and see whether there's a particle going through that slit or not, they're all the same. You see, everything is just probability until you make the measurement. Make the measurement means look at the woods and see what's there. Make the measurement means look out in the universe and see what you find. Make the measurement means put a detector here and see where the particle is. That's making a measurement. Bringing data, information into this virtual reality. And remember we said once the information gets here, it has to stay here. It has to be consistent. You can't have two people walking into the woods, one right after the other, and one sees palm trees and the other sees pine trees. That won't work. Once the first guy says and pictures are taken and things are done, then that's it. That's the way it is. The information's here. Reality must be consistent. Part of the rule set. So what happens is, if we look here and we know, and we put a detector here, and we see a particle, well, now the larger conscious system in a data stream of the person who sees the particle, which his instrument, it's the same thing, says, okay, what's the probability that the particle's there? We're going to make a measurement. All right, probability of 1, the particle's there. Guess what? We got a particle. A particle now exists there, and because the measurement was taken, the probability wave was collapsed. Physicists call that collapsing the wave function. The wave function is a probability wave. Nothing's waving. It's just a probability wave. It's just a mathematical way of treating this problem. So we collapse the wave function, we get a particle. And once you've got a particle, that's information here. It stays here. What does a particle do? It travels in a straight line. That's all a particle can do. If you don't make the measurement, then it's still probability. That woods was still just probable before the guy walked into it. Whatever was in the universe where that telescope looked was just probable. It wasn't really there. We do not live in a physical, objective reality. We live in a probabilistic reality. And that's what they discovered here when they did this experiment. It was a probabilistic reality. So it's just probability until the measurement's made. Now, what's key here is information. When they did this, they had all kinds of people kind of making conjectures as to what in the heck was going on here. And some people said, well, it's consciousness that does it. It's consciousness that makes this measurement, and if a consciousness, it collapses the wave function and creates the particle in this reality. So that's the idea, that's the, that was one idea of how it worked. Another group said, no, it's not really the consciousness is the thing, it's the measurement. It's when you actually make the measurement and get the data, that's the important thing, you see? And it's not really the measurement either. It's the information. Because you see, you can let these detectors run and make the measurement. It's just that you don't collect the information. And you get a diffraction pattern. You see, it's still probability. Doesn't matter whether the measurement's been made or not. It matters whether the information is here. Because if the information's here that it's a particle, then the only consistent thing to do is to have a particle that travels in a straight line. If the information is not here that it's a particle, well, there's nobody asking for a data, in their data stream to say anything else. It's just still probability. So you see, it's not really, in physics it's called the measurement problem. If you Google the measurement problem, you'll find all sorts of stuff about this. Like I say, it's been around since the 1920s. So the the measurement problem really isn't a measurement problem at all. It's an information problem. When the information comes into this reality, then it would be inconsistent to say, well, the information says there's a particle, but it doesn't travel in a straight line and hit what's behind it. That's what particles do. You see, we have an inconsistency, not allowed. So when the waveform collapses, you get a particle. It acts like a particle. If it don't get that information, there's no information to show that there's a particle there, it's still probability. How long? Until it gets here. It stays probability. Now here the measurement is made because that particle hits something, and there's a detectors here, a film. If it was light, there was film here, and that light would make a little spot on the film. Or there's some kind of other sensitive material to find electrons and buckyballs and all the rest. They have sensors out here to find when they hit. So when it hits the screen, then a measurement's made, right? Because it leaves some data. Well, what happens is that when it goes into it's still probability. It goes through both the probability, we say the probability goes through both slits, but that's just metaphor. It's just probability. It stays probability until it hits here. And when it hits here, what happens? Well, it gets to the screen. It's still this probability. It could be anywhere. It could be any of these places. Reach up with a random draw into that probability distribution and say, well, where's it likely to hit? There. Next one comes in, draw up another random draw. Where's it likely to hit? Bam, hits there. Another one, where's it likely to hit? It may go back up to that one. And so on. You just keep collecting them one at a time. And they do this experiment now, and you can see it. All this is visual. They've got a laser, and they can pump out one photon at a time, and you can actually see it here accumulate on a computer screen as the detectors accumulate, and you'll see a little spot of light there, and then a spot of light here, and then one here, and then here, and then there, and then there. It's just randomly they add, and after they've put thousands and thousands of them in one at a time, you've got this spot, 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 and so on. That's because it's just filling in this probability distribution, which is what you calculate if you have two sources of probability interfering with each other. Okay? So that's an old experiment, been done now tens of thousands of times, and every major university on the planet has done this. It's not that hard of an experiment to do. In the 1920s, this was a really hard experiment. Now, with lasers and the kind of control and the sort of sensitive films that we can create and the computers to collect the data, this is an easy experiment to do, and it's done. You can go to the web and Google double slit experiment, and you probably get enough reading material for 3 months. It's just everywhere. So this is not like some crazy thing that I just thought of and people still argue about today. This is fact. It's been a fact for 80 years. It says reality is probability before one collects the information. One has to get some information in a data stream to make it one way or another, random draw out of the probability distribution. It joins our reality. Okay? You see, it's not just a crazy idea. Physics says this is the way the world works. Now, we've done a lot of other things. We have entangled pairs, we have all the rest of this, and it works exactly the same way. It's answered in exactly the same way. So we have science that does this. And when we crash atoms together and we get results. We've done, like I say, these entangled pair things where you have a spin up here and you have this pair. So physics likes balance. So when you have these particles and they have a neutral spin, they're balanced. There's a spin up and a spin down. And if this one goes that way, that one goes that way, because conservation of momentum says they have to point in opposite directions, so they have a zero angular momentum. So you take these particles, these two particles, and they're entangled, and you move them apart like this, and now they're way far apart, and they flip one, and the other one flips instantly. And they say, oh no, that violates Einstein's relativity, which says light can't travel more than c, a certain number. Light can only go so fast, and it always goes that speed. It's constant. Light always travels that speed. And yet these two things flip, so that light couldn't have gone from here to there. Nothing could have gone from here to there and told this one, hey, it's time to flip now. You need to turn over your twin over there. Your entangled twin turned over, now you need to. They would have been delighted if that had happened, but it didn't. When one flipped, the other one flipped right away. Why is that? Because the two of them together, we think of them as two separate things because they're in two separate locations. It's just one thing. It's a system. In probability, it's a system and one thing, and when you flip one, you flip the other one. It's not two separate things. Just because one is 100,000 miles away from the other, it's still one thing. You see? So that's the way science has told us, and all these things, the two things flipping, the entangled pairs, all of this comes out of the same mathematical theory called quantum mechanics that assumes particles are probability distributions. So all of this was predicted, and we knew theoretically that this entangled pair was something that might happen, and there were lots of arguments about it 50 years ago, said that's impossible. That shows you the quantum mechanics isn't right, because that's just impossible. You get two things, they won't do that, it won't happen, and then about, I don't know, it was probably like 20 years ago they did the first experiments, and it worked exactly like quantum mechanics said. Particles are probability distributions. Now, how does this work for us? What does this mean? We've got a virtual reality, and the virtual reality is evolved. And in order to evolve a virtual reality, there's a couple of things you need to do. Like we said, we need to know what to expect. We need to know what's happened, because the point of this virtual reality is that it be consistent, that it provide good, consistent feedback to the students in it. That's us. Okay, so you have all the information of everything that could possibly happen. Remember, it's a probabilistic reality. So the calculation in this virtual reality, the server, if you will, that's calculating this, calculates all the possible things that might happen next. Now that's a lot of things, but it's finite. And the consciousness system is pretty big. So it calculates everything that could possibly happen next and the probability that each one might happen next. So that's what we call the historical database. But that historical database, of course, flows from a future probability. It also calculates everything that could possibly happen next and the probability that it will happen next. Now, how does it do that? Well, it's got all the history. You see, it's got all this history of everything that has happened and how the probabilities were picked. So it says, okay, given that what happened before is likely, we can come up with probabilities of the stuff happening. So it has this, everything that could possibly happen next and the probability that it will. And then say, given that that's true, we can go out one more time increment and say, well, if that's true, what would have happened before that? And if that's true, what would have happened before that? And what's the probability? And so it can work its way out into the future one step at a time. Now, where are these steps coming from in this time? This is a simulation. Those of you who have worked in simulations know that the outer loop of a simulation is called the time loop. And what happens is you have, in a computer, you say, okay, here's time t equals 0. And now you have time t equals 0 plus some little increment. You do all the calculations with the change in the time, and that's a new state. Then you increment time again. You go through this time loop. It's like a do loop. And you keep incrementing time, and every time you increment time, you go calculate everything. So let's say you're calculating a ball flying through the air. Well, t equals 0, ball's here, has a certain velocity. T equals the next delta t, it's here. Next delta t, it's here. Next delta t, it's here, and so on. So you simulate this ball traveling through space. And if your simulation has a big time increment, then it jumps. Big time. If it has a tiny time increment, it just moves such a tiny little bit that it seems continuous. So we know that in our video games, right? If the video games are cheap or they're not well developed, we get characters that move like that. It's jerky. That's because that's only calculating here, then it doesn't calculate the next one until here, so it just jerks from there to there. So we get that jerky motion. But if they calculate it every tiny little bit, then it looks smooth. Same way with movies. Movies are a bunch of stills, right? Each frame of a movie is a still shot. But if the still shots don't have much motion between them and you run them fast enough together, then it looks like fluid, smooth motion. It's the same thing. So we have this future probable database that goes along with this virtual reality. All the things that could possibly happen and the probability that they might. And that works its way out for as many of these delta t cycles as the system wants to work it. Now, each one, every time you do the next delta t, you have an assumption that the last one was what was actually going to happen. So you build the next on the last and so on. So the further out you get, the rattier it gets, the less likely it is to actually happen that way. So now we have the delta t goes around the loop again in this simulation, and that's, choices are made. We're here to make choices and to grow up by those choices. We make the choices, and that defines what actually is going to happen. We could have made different choices, and if we had, we'd have gotten a different future. But because we make this choice, then we all together kind of actualize what happens in that next delta t by making our choice. And that then becomes what did happen. What didn't happen were all those things that could have happened but didn't. That moves to the past. That becomes our next increment in the past. So you see how we have this thing? We have all these probable futures. We have a present where we make the decisions, and then these probable futures after the past move through, and we have all the things that actually happened and all the things that could have happened but didn't, and the probability that they would have had. So this big database starts in the future, All the action, all the free will is executed in the present. That's where all the action is. The rest of it is just calculation to support the virtual reality. And then you have the past database. Okay, so that's how this works. When you make a measurement, whether it's that looking out into space or whether, what the woods looks like that you look at, or at the slit of a double slit experiment, you're making a measurement and there is a probable reality. There's probabilities, this next delta t. And as I told you earlier, you can modify those probabilities. Those future probabilities can be modified with intent. Now here in the double slit, nobody's really trying to modify anything. They just get what's probable in the next time, and these particles will just line themselves up in this diffraction pattern if nobody's looking, or they'll pile up in two little piles if somebody is. Now when I say looking, I mean recording the data, taking the information into this reality frame. Okay, so I guess the bottom line here is a couple of things. One, science, physics, over the last 80 years has confirmed that reality is, as I'm telling you, that reality works this way, that it's probability, and that things come into this reality when we make measurements, when we take the data. Again, it's not the consciousness, but a consciousness is required to make the measurement. It's not the measurement, but a measurement is required to be taken. It's the data that's brought here that becomes a fact of this reality, that there is a particle there. Once that fact is here, that piece of information is here, then we get a particle, or we get a dead tree wobbling, or we get a supernova in the universe, and then it stays that way. Can't do anything but go straight across and hit the screen on the other side. That's what particles do. See? So that's the physics of it. So this is not only kind of weird metaphysics that I've been telling you, this is weird physics as well. But it's a standard weird physics. Every physicist on the planet will explain that more or less the way I did. That's kind of the way it works. So here we have this future probable database. And in this future probable database, there's all these arrays of what might happen and the probability that it will. And it goes out a pretty long way. Now that's just data in the system, just like the past database is just data in the system. We're consciousness. We don't have to be stuck here in this virtual reality just plugged into this one data stream. We can leave. We can go look at other data streams. We can sample those databases. We can get around in those databases and look at the data and play with them if we want, because we are consciousness. We're not a physical body, with somehow a magical consciousness living in it. We are a individuated unit of consciousness with a physical avatar that is experiencing and doing, basically following our instructions. We're the awareness. We're the mind behind the body. We're consciousness. Okay? So the brain does not create consciousness. The brain's just a virtual brain, just like it's a virtual body. If you had a Sims character, and that Sims character was a brain surgeon, and you went with him to his Sims hospital, and he had a Sims patient who had some kind of a brain problem, and the Sims character, cut open the skull, what would you see? You'd see a brain, right? Because the people doing the Sims simulation would simulate a brain. Because suddenly, when you open up a skull, you need something in your data stream. So you get a brain in your data stream. Close the skull back up, you don't have a brain in your data stream anymore. The brain doesn't need to be part of the data. But the probability of what's going on is still there. You see, the probability is still there. It's only when you need the data that it gets manifested here. The rest is probability. All right, that's kind of well, there's one other thing I want to tell you. There's another big part of physics called relativity. Right now, you have quantum mechanics and relativity. Between the two of them, they pretty much do everything in physics. There's also, Maxwell's equations in electrodynamics, but they actually get described pretty well by quantum mechanics. So you've got these two big sub-sciences in physics. And they both have a mystery. Quantum mechanics mystery is, as Feynman says, we just don't know. Shut up and calculate, it's a mystery. Why should particles be probability distributions? Makes no sense. Now in relativity, there's another big mystery. Relativity, special relativity was produced by Einstein, again, back in the 1920s. 1920s were a very productive time for physics. Hasn't been that productive ever since. A very productive time, and he made an assumption, just an assumption, had no data to back it up. He made an assumption that the speed of light is a constant. Just a constant no matter what. Now you'd think that if you had a source of light, say a flashlight, and this flashlight was traveling very fast, and while it was traveling you turned it on, that the light would actually go the speed of light plus the light of the flashlight. Things in our world all work that way. Velocities add. So you're riding in a car at 10 miles an hour and you have a ball in your hand and you reach out the window, you throw a ball another 10 miles an hour. Well, when that ball leaves your hand, it's really going 20 miles an hour relative to the ground, right? Because it gets 10 miles an hour from the car, 10 miles an hour from your throw, and those add together. Everything in this physical reality works like that, except for one thing, and that's light. Light doesn't work like that. It doesn't matter how fast the source is going, light always goes the same speed. And physicists at the time thought that Einstein was nuts because there's just nothing ever worked like that. It's magic. Why would it be like that? Einstein says, well, let's assume it is. He did a calculation, and his calculation turned up a bunch of really crazy stuff. The crazy stuff in relativity, in special relativity, are that when something, if I have a pen here and it's traveling like this, the faster it goes, the shorter it gets. And when it gets to the speed of light, it disappears altogether. So the speed of light is a singularity and you can never get there. Another thing, this pen, if it's going real fast and it only gets shorter in the dimension of the same dimension as the velocity. This width stays the same. Now, if this pen is going and it gets faster and faster as it approaches the speed of light, it gets more and more mass. So we would think that in terms of heavier and heavier, until at the speed of light, the mass goes to infinity as another singularity, and we just don't go there. Okay, so there's these odd things. And the third odd thing Einstein calculated is that if you're on this pen and it's going, and the faster and faster it goes, the slower time goes. If you're on this pen traveling, that time slows down. Matter of fact, it slows down so much that if you had two twins, it's called the twin paradox, again back in the 20s. If you had two twins and you put one of them on this rocket ship, put one of them on this pen, and one of them stays here, and the other one goes off at 9/10 the speed of light, and does that for, say, years, turns around, comes back at 9/10 the speed of light, and the twin gets out, and guess what? The twin that was in the rocket ship has hardly aged at all, and this one is, say that trip took 10 years. This other one's 10 years older. This one's maybe 10 days older. Okay? So if you make a real long trip, this one's already died of old age, this one's come back and only a year or two older than it was when he left. It's called the twin paradox. It was a real famous thing in physics back in the 20s. Well, everybody that looked at that stuff from Einstein and his special relativity with this crazy idea that light is invariant under the speed of its source, and they said ridiculous until experiments proved that he was exactly right and that everything he said works that way. And they do these experiments with little particles. They take very precise clocks, cesium clocks that measure to the billionth of a second, and they spin them around in satellites and they bring them back and look at it, and the clock's slow. These clocks don't ever get slow, you see. Time has slowed down. So they measure these things. When they do the big atom smashers, like over at CERN, they have these particles that's zinging around in a big circle. They get up to near light speed, and when they do, they have to calculate that these particles are getting shorter in that dimension, they're getting heavier and heavier, okay? And time is slowing down. And if they don't do those, what's called relativistic calculations, they can't get them to spin because they can't time their magnets right. So we know that Einstein was right. That is the way this world works. So you see, physics now are telling you that particles aren't really particles. Reality basically is probability before a measurement collecting data brings it into this reality, just like I told you about the tree in the woods. They told you that back in the 1920s and you didn't know. And same time frame, they told you that things would get heavier, shorter, and slower, as they sped up. And this has been a standard part of standard traditional physics since that time. Well, this is a virtual reality. Guess what? It increments by 1 delta t, 1 time unit, every time the time loop is run. So you change time, calculate again, change time, calculate again. That's how we move, right? We move in time because the time loop keeps changing. And speed of light is basically as fast as information can travel, going from one digital chunk to the next chunk to the next chunk. In other words, our reality is not continuous. Now we know that in everything else. We know that the table in front of you is not continuous, right? It's a few little particles with a lot of empty space between them. That's the way atoms are, and molecules are little bits of matter with lots of space between them. So most of that table in front of you is empty space, and it's moving and it's vibrating. It's got all this stuff going on. Now to us, it's just a static table. And we know that quantum physics describes all those particles. They can only be in certain states. They're not continuous. Well, time is also not continuous. It comes in little chunks. Yes, our reality does move a block at a time. It's just that the times are so short that it seems continuous to us. And space is the same way. Space is not continuous. Space comes in little chunks. And the traditional physics will tell you that the Planck length, which is a very small length, named after Planck, who did this work, that space becomes granular. What that means is it gets digital. This is a digital information system. And because it's a virtual reality, it's calculated in a time loop. So you see again, physicists knew 80 years ago that at the Planck length, space would disintegrate into discrete chunks. But they didn't know what that meant, so they just said, well, that's just more of this crazy stuff. Shut up and calculate. Well, obviously, that's what happens if you have a digital simulation. You get discrete chunks of time, you get discrete chunks of space, and for every discrete delta t, the fastest anything can go is to move from this chunk to the next chunk. The next delta t, you can go from that chunk to the next chunk, you see? So moving one increment of volume every increment of time is as fast as anything can go. You're not allowed to jump 10, that's called teleporting, and that makes this a kind of a funhouse reality. You need a consistent reality. So that's why the speed of light is a constant. It can only move from one increment of volume, one increment of space, to the next increment of space in 1 delta t. Nothing can move between delta t's. I mean, everything is static until a delta t comes, and in 1 time increment, it can move 1 space increment. And it doesn't matter how fast the source is going, you just can't get any faster than 1 space increment in 1 time increment, therefore your speed of light is constant. You see, another big mystery solved. So just by seeing this as a virtual reality, a lot of these physics problems just resolve themselves. We have a problem with the Big Bang. Okay, what came before the Big Bang? See, if you think that this is a physical universe, then there's this problem. Okay, the Big Bang was a little ball, high pressure stuff, and it expanded, and we ended up with the universe. We've all heard that story, but where did that little small ball of stuff come from? How did it get there? It didn't come from our universe, because our universe hadn't evolved yet. It didn't exist, you see? Well, where did it come from? How did it get there? Well, just shut up and calculate. You see, we don't go there. We don't go there. Well, think of your elf in World of Warcraft. If your elf were conscious and he wanted to find out where did his World of Warcraft world come from, where did it start, what would he find? He would find that just all of a sudden it was there. Just popped out of nothing, it was there. Well, when did this World of Warcraft start? when they hit the run button on the server and started calculating that reality. Well, that's the same with this. The reason you can even say this is the fundamental way. Somebody says, well, how can you tell us the virtual reality? And you say, well, one of the most fundamental characteristics of virtual reality is you keep looking at your history back and try to get to the beginning, and you'll find that it just starts out of nothing. That's the way virtual realities are. When the run button's hit, it starts to calculate. There was nothing before, and now you've got it calculated along. Well, guess what? It's exactly the way physicists see this reality. You get back to a point, there's a Big Bang, and before that, what? Nothing. We just started there and went from there on. If we start there, we can do the rest, but you see, we just started out of nothing. So here you have these physicists all these years who really did test metaphysical and mystical things, and their whole concept of this reality is mystical. The little plate ball of energy and pressure, whatever, just happens out of nothing. So science for the last, I don't know how many, 100 years, has basically been based on a mystical assumption that we started out of nothing. It couldn't come from this universe, because this universe hadn't been created yet. So where did it come from? It had to come from outside of this universe. Well, the L says the same thing. It just started one day, so it must have come from elsewhere. There's a very significant physicist, this Dr. Edward Fredkin. He's still working physicist, still does very good work. MIT, Boston University. I can't think of where he went after that, but anyway, a high-powered physicist, well-respected. And in late 1990s, he looked at physics and said, everything we see is discrete. All the particles, everything that we understand, everything that we can measure actually is discrete. There's only two things that aren't discrete, and that's time and space, and we think they're continuous. And he said, I'm betting they're not. They're discrete too. We just don't have the ability to measure fine enough to see the discreteness. So he started with that theory, ended up with a conclusion that we're living in a virtual reality, and that this virtual reality had to be computed somewhere else. And he named that somewhere else other, and he put quote marks around it. He said, because a simulation doesn't simulate itself, can't create itself. You see? It has to be created by somebody. So the World of Warcraft didn't just suddenly start running on a computer. Somebody had to create it. A simulation has to come from somewhere. So he said, well, this is a virtual reality, and the physics shows that, because he saw all these other problems were solved by virtual reality, and he said, and the source is other. It comes from other. And then he said a little bit about what some of the constraints on other. But you see, the same thing with the elf. When the elf gets to the point where it just happened, he has to come to the conclusion that it came from other, because it can't compute itself. That's illogical. So, other. Who's the programmer, you see? Well, the who's the programmer is not the who. It didn't just get programmed. Too much to do. Every blade of grass here needs to be programmed, you see, and how it waves and so on, way too much. So it's a probabilistic simulation created by the larger consciousness system to give us individuated units of consciousness, a schoolhouse where we could evolve, which means it could evolve. It doesn't just do this for us. We're here to help the whole system evolve. So you see how all this fits together and how it explains physics? The two biggest basic mysteries of physics are the speed of light being a constant. Simple. It can only move one increment of volume for every increment of time. What about these particles of probability? Everything's probability. So was that big, galactic thing that the telescope saw. It was just probability until the telescope made the measurement. Then you draw from the random distribution, you get a result. Now that's here, it stays. Same for the guy walking into the woods. Now there's another little trick about this probability that's interesting too. Let's say the guy walks into the woods, he sees the wobbly tree, and he leaves. Well, we can just do it right at that point. He leaves, and as he walks out of the woods, there's a big bear there, and the bear swallows him. He's gone. And if he took pictures, the bear swallows the camera too. The information's been erased. Now there's another guy, the next day, comes, bear's not there anymore, he walks into the woods, and will he necessarily see the same thing? No. There's no information here any longer that would create an inconsistency if he saw something else. So it's gone, the movie title, it's gone Back to the Future. It's gone back to probability. So the second guy walks into the woods the next day, and he may or may not see a dead tree standing there, because again, probability would be drawn out because there's nothing here to define it yet, and whatever gets drawn out, that's what he'll see, and that's what'll be there, you see? So information can come and information can go, and if it goes, then you're back to probability, and quantum mechanics has demonstrated that. That's a scientific fact. They're called quantum eraser experiments. And I can show you one on the board, but it's kind of complex, and if you don't have a colored thing with all the, nicely drawn, I'd probably just confuse you more than not. But here's the way it worked. We said that those detectors could just continue to detect, but we'd ignore the information, right? Nobody would collect it, so it would just disappear. Just unplug the recording devices, it would disappear. Well, what they found out is that they can record that data. So now it actually is recorded. That would mean that they know what slit. They could look at that data and find out what slit that particle went through. And they should have just 2 piles of particles behind each slit. It's all there and it's done. Okay. Now let's say they did 2 experiments. They did 2 of these experiments, identical, one after the other. They did one experiment, they collect all the data, and here it is sitting, and nobody's looked at it yet. And they get another experiment, exactly the same. They put particles through the 2 slits, they had detectors, they recorded and the information. So now we know in theory that both of them would just have 2 spots where the things went through the slits because we have the information what slit they went through. Well, so they take one of them and they open it up and they look at the data. Sure enough, it's exactly what they have. They have 2 spots where the data went through. They take the other one and they say, well, hey, before we open this up, let's take this envelope that has the recorded data in it and burn it. Now these 2 experiments were done exactly the same way in the same time. So they take that envelope that has that recorded data in it and they erase the data. They burn it. That data doesn't exist there anymore. Now they open up the envelope that has the screen in it, and what do you think they see? A diffraction pattern. You see? Now it's a diffraction pattern. Had they not burned it and they opened it up, they would have seen 2 dots. But because they burnt the information and the information's gone, they see a diffraction pattern. Eraser experiment's been done hundreds of times. It's a piece of physics, you see. And they erase the data after the experiment's been completed. So you collect it. You see what I'm saying? It's very strange, isn't it? You didn't know reality was that strange, but that's because you're not physicists, maybe. If you were, you'd know that it was strange, but you wouldn't have any idea why, and you'd say, just shut up and calculate, and don't worry about it, nobody will ever understand it. But that's the way physicists have treated the problem. This idea of virtual reality solves all those problems, and it all makes sense now. That's why today I'm not on the fringe anymore. I'm sitting more the center of the physics world, because everybody has kind of gotten the idea, yeah, virtual reality, this makes a whole lot more sense. It answers a lot of our questions. And there's been any number of studies where they take physics and they say, all right, let's have the assumption that this is an objective reality that just exists, and here's the assumption it's a virtual reality. Just look at all the experiments and all the physics and see which one does a better job of explaining it as a better model. And every time it comes out the same answer. The virtual reality is better physics. So now we have to look at this and say, okay, this is a fact of our life. Physics has told us this is the way reality is. What does this mean to us? What are the logical ramifications to us of this? You see, physicists don't go there because that's philosophy, and they don't do philosophy, they just do physics. So we have to look at this and say, how could this happen? There's also this problem in biology about consciousness. Consciousness has several problems, trying to explain consciousness. And they have one problem that they have defined as the hard problem. And if you Google the hard problem, or even consciousness, you'll find this hard problem. What's the hard problem? The hard problem is, how could consciousness, something like consciousness, be created from basically organic matter? How do you take a computer, even as a biological computer, how do you take neurons and little electrical signals and end up with consciousness, a decision maker, a choice maker? And they can explain consciousness, other aspects of consciousness, but that aspect of consciousness is the hard problem. And just like the physics here, that it's impossible. Just forget it. You'll never solve that problem. It's just beyond our scope. Well, you see, it's very simple. The reason the problem's hard is that they're looking at it backwards. The brain doesn't create consciousness. Consciousness creates the virtual reality in which you have a virtual body and a virtual brain. See, the brain doesn't store or compute anything. All that's done in consciousness. The brain simply provides the constraints, just like the rules in World of Warcraft provides the constraints of what your player can do. So here we are, and somebody sneaks up behind us on a dark night and hits us over the head with a lead pipe, and we have brain damage. What has that done? It has changed the constraints that we, the consciousness, have to work with in our avatar. So now our avatar kind of, maybe can't use one side of its body very well, or whatever else. It just changes the constraints. So, it's just looking at the problem differently. Well, of course, the brain creates consciousness, because if you hit the brain, you change the consciousness. I can go in and do these different things to the brain. I can do a lobotomy, or I can cut out the lobes that do vision, and you go blind. So of course the brain must create consciousness. No, the brain just creates constraints in a virtual reality by which we have to play by those rules. So you see how you get the same result with just a different perspective? Except now, your perspective solves all these physics problems. Another physics problem we have is the universe is expanding. Well, there's a logical problem, because traditional physics say this universe is all the reality there is. But it's expanding. Into what? How does all the reality that there is get bigger? Well, it's another one of those mystical things. It just happens. It just keeps growing. Space just somehow makes more space, and we don't know. Just shut up and calculate, We get to that same point. Well, in a virtual reality, a bigger expanding universe is just a bigger number, right? I mean, you can write the equation of a sphere in a laptop and let it iterate the size of the radius, and you can have a sphere that's 1,000 times bigger than this universe very quickly. This is math. It's just numbers in a computer. There is no space, you see. There is no space. There is no distance. It's information, consciousness. So all of these things lead you to this conclusion, if you're an open-minded scientist, that consciousness is the computer. You see, now we've solved not only the problems in physics, but we've solved the problems in metaphysics and the problems in theology. And the interesting thing is that all of these things connect. What do we learn? We're all netted. We can communicate. We're connected to each other. What do we learn? Our point of being here is to grow, lower our entropy, become love. Okay, that's what we're trying to do, to get rid of the fear, get rid of the ego that's caused by the fear. The Buddha says, we're all one. he also says that this physical reality is just made up. It's not real. This is not the real world. There's this unseen world that's the real world. Well, metaphysicians have been saying that for, millennia, and we don't really understand it. It sounds like, it's that woo-woo stuff that doesn't really make sense. It's right. So God is love. Yes, that's right. You see, all these things that are kind of out there that we know about, well, that's right. Well, we know the mind can do lots of things. There's a thing called the placebo effect. Okay, most places you can't market a medicine unless it can beat the placebo effect. The placebo effect is if you give somebody sawdust or sugar instead of the medicine, that the medicine will work and the sawdust and the sugar won't, you see. Well, what they found out is that the sawdust and the sugar often works better than the medicine. Why? Because you've told a person you're going to give them something that will make them better. Now they have a positive intent. That positive intent changes the probable future, and they get better. It's called the placebo effect. We know that from all sorts of things. There's lots of studies. A teacher is told that she has the dumb kids. Another teacher is told that she has the smart kids. But really, they're the same bunch of kids. They were just randomly selected. The one teacher that has the smart kids, their kids do better, make better grades. We have an intent. Changes reality. And then you tell the kids, oh, you're the dumb kids and you're the smart kids, and now it's even a bigger gap between what those kids do. They're the same kids, just randomly selected out of a bunch of kids. You see, what we think has a lot to do with what happens. We can heal with our mind. We know that that works. We can visit these reality systems. We can get into that future probable database if we know how, and look and see what's probable. Well, we have little old ladies who read tea leaves and do other things, and they know what's probable. And some of them are really good. They're accurate because they're just connecting to a database. People have precognitive dreams where they dream things that didn't happen. Why? The data's all there in a database. You just have to know how to access it. People get connected with things in the past. They talk about past lives and things like that. Well, the data's all there in the database. So all these things that are kind of in our reality frame, you see, now start to make sense. So we not only can see the physics behind why you can heal with your mind or why the placebo effect works, but you understand, the point, where did it come from? Why are we doing that? Why do we have that ability? How do we get that ability? And once you understand it, then you can get rid of all the ritual and all of the, drama that goes with doing these things. It's just an intent that is querying the database. So suddenly now our metaphysics starts to open up. What about remote viewing? That's a science now. People have done remote viewing. Even the military and the intelligence people, they do remote viewing because they know it works. They're not kidding themselves, make these expensive programs. They know it works. So we know that's a fact. How does that work? It's just intent, collecting data from the database. Sure, you can remote view and go and see what's going on. Count the number of people that are standing on top of the pyramid today, at a certain time, and have somebody take a picture and see if that's right. And remote viewers can do that sort of thing. And they used to be stuck just remote viewing here in this reality frame until one day some of them by accident realized that they didn't have to stay in this time and in this space. Then they realized they could remote view to the future. They could remote view to the past. And they were coming up with all kinds of things that were proven these are correct. And everybody can do these things. It's not just special people with special talents. And when we get to, how are we doing on time? Oh, I'm about the time where I need to quit. When we get to tomorrow, we're going to talk about all these things and how they actually work and how you can learn. Because what I will tell you is that belief is one of the big problems. Fear and the ego that fear creates, and we'll define ego and that kind of stuff later. But fear and the ego generated by fear are big problems. Belief is also mostly generated by fear, and it's a big problem. The reason it's a big problem is that once you believe you know, you have a much lower probability of ever knowing, because when data comes in that's outside of your belief, you shut it out. It's gone. It's just like, well, that's a mistake. That's a that didn't happen. It's like throwing away data that's an anomalous. Anything outside of your belief is an anomalous data point that you toss out. So you get trapped. And in my books, I call it a belief trap. You get trapped with your beliefs. So I don't, and I tell all my audiences this, I don't want you to believe anything I'm telling you. I don't want you to disbelieve anything I'm telling you. Please don't believe me. If you do, that just won't do you any good. That will be an understanding in the intellect. If you say, well, that's a lot of trouble to have this experience myself, so I'll just believe that he knows what he's talking about, and that'll be all right. Well, you will come to an intellectual understanding then about the way the world works. But it's just in the intellect. It's not going to really do you much good until it gets down at the being level, that you can incorporate it as part of your life. And the only way you can do that is through your own experience. If it's not your experience, it's not your truth. So don't believe me, but be open-minded. Don't disbelieve me. A disbelief is just another kind of belief. Neither one of them will take you anyplace important. If you just disbelieve it, and that's just a bunch of nonsense, then you no longer pay attention, you no longer process it, so you shut yourself out. Well, that belief isn't useful. If you just believe it, well, you may get some intellectual information, but you can't really use it. You can't make it a part of you. You can't learn to heal, to remote view, to grow up, get rid of your ego. All of it's just up in your head, and none of it's where it counts. So it's not a matter of belief. And you come here with the idea that, that I can show you, let's say, the non-physical. I can show you things that are outside of this reality. I can't show you those things, but I can teach you how to find them yourself, how to experience them yourself. But I can't experience for you. You have to experience for yourself. And until it's your experience, it's not really real to you. It's just this mind game.